Thank you everybody for coming. Today I will talk about compilers, virtual machines, and code analysis. What makes Dart and Flutter run? So usually when I pitch this talk, I explain it by, we'll talk about a bunch of things that you don't usually need when developing, but which are nice to know and understand how the underlying language works. About me, my name is Norbert. There's my X profile you can scan and see what I'm up to. In the past, I've been working on a bunch of projects which involve different kinds of involvement into some kind of analysis or some deeper understanding of how Flutter works. One of those was the original Flutter IDE, which was this visual editor, like kind of some sort of predecessor to Flutterflow. I've also worked on Detective, which was or is a real-time debugger that uses some APIs that the Dart VM exposes. And recently I built a small project to visualize widgets of Flutter, which also used some kind of code analysis and code generation. So, but enough of this, let's dive right into the talk. First off, we need to understand how computers actually work before we can look at what Flutter and Dart does. For this, buckle up. The next half hour will be a lot of theory. Of course, I'm joking. We don't need to understand how modern computers work in detail. There's a bunch of complexities, a bunch of things that are not really important, which are mostly there for performance optimizations, for security, and other things. Programming or computers in general are actually pretty simple. So just a very simple example of a program, which is less useful, but it's a program, is let's say we want to take a number 1, we want to take number 8, put both of those into boxes. And then we want to tell the computer, okay, just add those two numbers up and put them into a third box. That's a program that the computer can execute. And if we look at some machine code, how that could look like, it's actually pretty simple. We take some number 1, number 8, and we tell the computer to add that up. So that is how machine code can look like. And that is something the computer can really understand and perform tasks on. You tell it very explicitly what to do. But when you're working on modern apps, especially in Dart and Flutter, you're not usually thinking about these low-level primitives of memory addresses, of registers, of pointers. You think in classes, you think in methods, fields. You execute code by calling functions, you print by calling functions too. So the question is, how do we go from our high-level representation of, we define widgets, we write high-level code, to machine code a computer can understand? And for that, there's a bunch of different ways how to go about it, but first way is we can do interpretation. So interpretation is a pretty simple idea where we kind of take the program as some sort of string and we execute some code based on that string. So let's say we have our program and we have another program reading the string and executing commands on behalf of that. The cool thing is we can just get it up and running. It is very portable. If that interpreter works on different computers, then our code that we write for the interpreter will also work on different computers. The downside is it is very slow, as you could imagine, because we're adding another abstraction layer in between executing what the CPU can understand and what we actually want to do. So to kind of address these issues, let's talk about AOT compilation. AOT compilation kind of involves a second step where instead of directly executing code, we first compile code to some sort of machine code. And that machine code is usually something that your computer, in that case, the CPU, can natively understand. So it compiles to, for example, on this machine, it would compile to ARM64 machine code. And then we execute that code by just running it and telling the computer, load that data, put it into the CPU, and do your thing. Cool thing is, it's pretty quick because we run on bare metal on the hardware. On the other side, one downside is very platform dependent. So there are Windows machines, there are ARM machines, Intel, there's so many different architectures. And if you do AOT compilation, you will kind of lock into one specific instruction set, one specific CPU. Then there is this weird mixture, which is called JIT compilation, which kind of takes ideas from both worlds, where we kind of do a bit of kind of interpretation, but also compilation. The idea here is we take our source code, and instead of fully kind of interpreting it or fully compiling it, we compile it step by step. So what we do is we first load the program, and then we just compile those parts of the program that we want to execute. Whenever we reach new parts of the program, we just compile new code. There's a bunch of cool things that this allows. For example, we can compile better code, because instead of just knowing what the program is, we also know how the program behaves. So we can make better optimizations. Also, Dart uses this for hot reload, where we can kind of replace code while the program is running without having to kind of do a full rebuild or anything similar. So those are kind of the main things that you usually think about when you compile code. But what does Dart do? So there's a bunch of different commands and a bunch of different things that Dart and Flutter can run in. So the first one is Dart run, which is just this very simple function that executes your source code. Internally, it does a JIT compilation. So it first starts a program, it compiles the necessary parts. Whenever it encounters new sections of the program which haven't been kind of visited before, there's a bunch of fancy algorithms for that. It will recompile or compile further. We also have the compile AOT snapshot, which is, as the name suggests, an AOT snapshot. AOT is used for release mode builds, for example, on iOS and Android. If you do a release to the Play stores, you have an AOT compilation. More specifically for iOS, you're actually not allowed to dynamically compile machine code. So even though it would be possible to kind of ship an application which is JIT compiled to the iOS App Store, it wouldn't be allowed because they don't want the security risks. The difference between AOT snapshot and the EXE is actually also AOT compiled, but the AOT snapshot doesn't include a runtime, so it's just code you've written. It doesn't contain a runtime which contains things like the garbage collector or other things that kind of make Dart actually work. And compile exe is kind of this handy, nifty tool which just packages everything in there and makes it self-contained and executable. Note both AOT and exe will make it platform dependent. So if you do exe for your ARM or Intel, you will have to do different builds. We also have a JIT snapshot, which is a pretty fun one. As you may have guessed, it does JIT compilation, but it does a kind of a dry run at the very beginning, where it executes your program and kind of does the first compilation step, where it does a startup. You can provide it some training arguments that should probably reflect how your program would be used. This mostly enables quicker startup because it doesn't have to do the very first compilation step itself. Dart compile JS. This is actually not really compiling, this is more transpiling, which means instead of producing machine code or some form of binary that can be executed, this produces code which is also very high level but in another language, in this case JavaScript, which then can be executed by browsers, which then do their JIT compilations and whatever. And yeah, this allows Dart to run on the web. And there's also a Dart compile kernel, which we'll talk about more a bit later. It's kind of this intermediate representation of how Dart program looks during its transformation. I mentioned web, of course. There is also WebAssembly, which is quite new. And with the recent addition of garbage collection supported in WebAssembly, Dart can also target WebAssembly really nicely. And that also allows it to run on the web. It has a couple of implications. I think there is also a talk either today or tomorrow about WebAssembly. So I won't really dive deeper into that. So, how does this all work? This works mostly in 2 steps, or that's how kind of it was architectured, in a so-called front-end and back-end. So when you, as an app developer, think about front-end or back-end, you usually think about an application on the front-end, like your Flutter app, and on the back-end you have some kind of server. In the case of compilers, usually the front-end is something that kind of does the first steps of taking raw text and transforming it into something more usable. Usually, or pretty much always, in some kind of tree structure, because those have really nice properties to work with. The backend is then responsible for taking that pre-processed structure and turning it into either some kind of JIT compilation, which you can execute, compile it further down to machine code, to assembly. And that's how it's done. And the connection between the front end, CFE stands for Common Front End, and the VM is kind of the back end, is this kernel file. And the kernel file is pretty much just a serialized abstract syntax tree. Don't worry about that. We'll look at this on one of the next slides. So the front end, what happens in the front end? Very first step, and there's a bunch of things you can do, so we'll kind of try to keep this short, is we have some kind of unstructured text and we want to make it simpler. So for example, if you encounter the void keyword, you really do not care about the letters V, O, I, and D, you care about the token void. So that's what the tokenizer does. It takes some kind of string, so a stream of characters, and transforms it into tokens. So in this case, you can see as an example, we have, imagine this as being a string, and it turns it into a stream of tokens which contain void as a keyword, main as an identifier, and then some parentheses and other fun stuff. After that, the big step is to turn that into an abstract syntax tree. So what is an abstract syntax tree? As the name implies, it's a tree which represents the program. So let's consider this very, very simple program, which is 42 plus 8. So the tokenizer would make sure that we don't have any white spaces in there, so we have 3 tokens. We have the number 42, we have the plus sign, and we have the number 8. So creating abstract syntax tree would result in something like this. You would have a binary expression at the top of the tree, and it would have 2 children. It would have an integer literal, 42, and another integer literal, 8. So the nice thing about this is if we want to, for example, evaluate this, all we have to do is, okay, let's see, how do we evaluate binary expression? We first evaluate the left child, which is 42, super easy to evaluate. We evaluate the right child, which is 8, and then we just add them both up. And the nice thing about the structure is that we can very easily nest it, and like the whole thing is very easily extensible. Let's consider adding another 42. This would result in a structure like this, and if we want to execute this, we already know how to evaluate a binary expression, so we can kind of recursively do a bunch of things instead of having to do some other weird stuff. Couple of other things that the front end does is things like type checking, for example. It makes sure that all your types match up. For example, if you try to assign an integer to a string, it will complain that's not possible, that doesn't make any sense. It does some type inference, where if you don't specify the type yourself, it will be smart enough to figure out, okay, you're assigning something to something that we don't know what it is, but we know the return type is a specific type. Also, some desugarings are implemented in the front end. What that means is basically some advanced language features will be simplified to simpler language features that can then be processed in a standardized way. And the result of all of this is, as we talked about, the kernel file, which is this .dil, which you may have seen if you looked into the build folder or some kind of things that are going under the hood. And that's just the abstract syntax tree serialized in a binary format. There's actually a nice document on GitHub that you can look up. It's explained how kind of the structure looks like, and that's pretty much it. If you're interested in kind of diving deeper into program languages and compilers and so on, there's this great book by Robert Nystrom called Crafting Interpreters. It's actually for free, it's available for free online, and he goes into great detail about implementing a language, implementing a tokenizer, an abstract syntax tree parser, and then a bunch of other stuff, so highly recommend if you're interested into this kind of stuff. But okay, let's go to the backend. So the backend is the second part of the compiler toolchain, and it has many functions, but in here I want to explore what happens after you have the abstract syntax tree and how is that actually turned into code that your CPU can understand. For this, I want to consider this simple function, which takes an integer, returns an integer, and essentially what it does is it adds 2 to it. So you can see there's 2 variables, both are initialized with 1, and it's added up. I also added a main function, which calls this function 50,000 times. And this is because the JIT compiler has multiple passes. So at the very first time it encounters a function, it compiles it, but it does so in a very simple manner, so it doesn't optimize it too well. By doing this, we kind of force the optimizer to kick in and create an optimized version of the function, which is just way less machine code for us to look at. We can use this command to compile and then also take a look at some assembly code generated by that function. If you're interested, there's a link on the Dart SDK that has some great documentation on how you can kind of inspect some source code. Okay, this may seem daunting and we really don't need to go into the details of what's going on here, but I kind of want to illustrate that what's going on isn't actually that hard. So I've highlighted both of the snippets kind of which are corresponding to each other. At the very beginning we have some setup. So the function is entered, we're setting up a stack frame, we're moving some things around, we're moving values around, where specifically the value I is moved to the register R1. And then the implementation of this function, which was originally 3 lines in our source code, was actually squished down to 2 machine instructions. If you ignore the second one, which is just checking for an overflow, it's just a single instruction. And what it does is you can see it adds 4 to, so it's adds 4 to R1 and saves it in R0. So you may think, okay, why is it adding 4? That's a great question. I wasn't sure either. So yeah, I messaged Slava on X, and he explained to me that the least significant bit is kind of used as an indicator whether a variable is boxed or not. And if you move all the bits to the left to make space for that, that means multiplying by 2. So this number 4 is actually the number 2, but it looks like a 4 because it's moved to the left. So yeah, it's saved to R0. R0 is usually, or in this case, used as a return register. And at the very end, it just does some setup, and it then calls return, indicating that the result of this function is an R0, which is just R1 plus 2, and that's machine code. So there's a bunch of different instructions which you can look up the specs for, but in essence, it's all it's using simple things, but of course, a big program will have a bunch of different machine codes. But anyway, a quick side note, because I find this very fascinating and interesting, there's this concept of bootstrap languages, meaning that some languages are implemented in themselves. So for example, these are some examples for languages where the compiler itself is written in a language of what it's trying to compile. You may notice Dart is not on this list, even though the front end itself is written in Dart, the back end isn't. And technically it would be possible to have a fully bootstrapped language where all of the tools and things that make Dart run are written in Dart, but the benefit just doesn't outweigh the investment cost of doing so. So Dart itself is not a bootstrap language, but I still think it's a very fun thing to think about. What usually happens is you write a first version of the compiler in another language, and once that's running, you can just toss it away and write a second version in the language that you already compiled before. Okay, we talked about a bunch of theoretical things. I want to get into a bit more practical. And, okay, first this. There's actually a package on pub which is called the analyzer, which is just something you can add to your normal Dart and Flutter application via the pub spec. And the analyzer, very much simplified, kind of is the front end. So essentially it uses the front end and exposes public APIs on things you can use to analyze source code and get, for example, an abstract syntax tree out of some kind of string. Just some boilerplate code you have to set up. You have to give it some files to analyze. You have to give it some context thingies, all very standard. And at the very end, you can get a resolved unit, which is basically an AST. So let's have some fun with this. I want to have a quick live coding session where we're implementing Dart in Dart itself. So we can switch over. Awesome. So in here, I already set up the dependency. I've written a few lines of code, but really not much. And what we want to do is we want to compile this function. So I've written it as a string. I can increase it a bit. Perfect, thanks. So we want to compile this function, which is a string, but it is a valid Dart program. I have a bit of code for kind of getting the resolved unit and getting the AST. And what we can do here is we can first create a visitor. So the visitor pattern is usually used when working with trees, as it allows us to implement some code that runs for every single node in this tree. So in this case, I've written a very simple recursive AST visitor that will call this callback for every function declaration there is. And we're kind of using this to find the main function, to get a pointer to that node. So what we can do here is instantiate the main function finder, give it the resolved unit and tell it to accept itself, and then at the very end, we should have a main function found. So now we want to execute this main function. For this, we can write another visitor. What was the shortcut? Eval, like this. So we want to write an evaluating visitor. So by the way, what we're doing here is a very simple tree walking interpreter. So we're not actually compiling machine code, but we're running very inefficiently on a very high level. But yeah, for the tree, for this tree walking interpreter, for implementing the evaluator, we have to evaluate a couple of things. In this case, we have function literals, integer literals, so the number 3 and 6 are integer literals. We have function invocations, which is calling the print statement, and we also have a binary expression. So for this, we can first implement integer literals, which are very simple to implement because we already have the literal value inside of there. After that, we can also implement the binary expression, which is also fairly simple because all we have to do is evaluate the left operand and the right operand, and then based on the symbol used to kind of mush these together, we just execute a different operation. And at the very end, we also want to implement the method invocation. We kind of do a quick hack where we just check if the method we're trying to execute is print, and if it is, we just print on the higher language, in this case, also Dart. So at the very end, what we can do is go up here and do a main function accept. So if the demo gods are with me, we should be able to execute this code. And we've implemented a very simple tree walking interpreter. So I hope you can see. I'm not sure how to increase the size. It says hello world in 9. Just to prove that I'm not cheating, let's add some numbers which I could not possibly script. Like this. Re-execute it. And again, this is a function literal. We're still inside a string, so all of this will kind of work. So if you want to verify, it should work. Cool. Oh yeah. that was a very simple tree walking interpreter, and you would really never use something like this for any kind of projects besides some kind of demo. There's actually a better way, and there's a pub package for that, which is called Dart eval, which implements a bytecode interpreter, which is still an interpreter, but it makes an optimization where it first creates bytecode, which is quite a bit more similar to assembly or like a lower language. And instead of like having a tree jumping around with pointers and moving all around the memory, it actually simplifies that by doing some pre-processing. And a more practical use case for this, interpreters are also one of the parts that power Shorebird, because if you want to do code push, as I said before, Apple doesn't allow generating machine code on the fly. So if you want to do some kind of new code or new behaviors that you want to kind of push to the users, you will have to use some kind of interpreter. So what happens? So for now, we've taken a look at what happens before Dart actually runs. So I want to give you a quick tour at a couple of magical things that the Dart VM does when Dart is running. And you may have seen this message before. This is usually printed when you first run your application. And what's nice or what's interesting here is you can see there's a debug service listening on and a WebSocket address. So this WebSocket address is actually something you can just connect to yourself, and there is a specification for it, and it exposes a bunch of cool and useful things of your running application. So this is also what is powering the DevTools. Here you can see you have access to your current widgetry of your running application. You can see values of variables, and you can even change things. Not in code, but actually in the runtime. This is actually also what powered Detective, which I quickly talked about before, where I had this idea that instead of setting breakpoints, I wanted to see variables change in real time. And I was able to connect to this WebSocket connection and just repeatedly poll the state of values and kind of see things changing and moving in real time without having to stop the application. That's all implemented in the VM services inside the Dart VM. How to use it? Super simple, not going deep into it. It's a pub package. You can put it in your Dart or Flutter apps. So you could actually implement or have a Flutter application that is debugging another Flutter application. Then you just connect to it, you pass it the URI, and there's a bunch of different cool methods you can call, such as listing all classes, getting instances of classes which are currently active. You can trigger the garbage collector and so much more. So for now, we're on Fluttercon. I think I pretty much only talked about Dart until now, so I also want to do a quick segment on Flutter. You may have seen this graphic before, which has been around for quite some time, and it kind of shows the boundary of what the framework is and what Dart does, and what the engine is and what C++ does. But I was wondering, where is the connection? What happens between the line? And so for this, I want to take a quick look at some code and show you what is actually happening if we are rendering a container. So for this, let me switch to this project. So this is just a Hello World project which I just freshly generated. In here we can see we have a container. So let's go in here. And we can see it's a stateless widget, so you may already know stateless widgets do not do anything by themselves. All they do is compose other widgets. So let's see what it composes. In this case, we're only showing a color, so it is actually relying on the colored box. So if we go into colored box, we can already see, okay, the colored box is no longer a stateless widget, but rather a single child render object widget, which means it has a render object and actually does some painting. So for this, let's move to the colored render box, which is its render object. This extends a proxy box, which just does some simple layering and sizing. But more importantly, it calls context.canvas.drawRect and paintChild too, but that's not too important. So let's see what happens if we go into drawRect. Okay, we are inside an abstract canvas class. In here, we can find the actual implementation on native canvas. So let's follow the trail. Okay, we're in drawRect. Let's go to _drawRect. and boom. Here we have a function which is marked as an external function. And this is actually using FFI to call into the engine, C++ world. So this drawRect is no longer implemented or is not implemented in Flutter itself. So essentially what Flutter does, it only composes, it does all the calculations, but the actual render operations, the actual, I wouldn't say heavy lifting because Flutter does most of the heavy lifting, but the actual painting is not done in Flutter. So if we go back here, what happens next? So we are in C++, we're in the engine. What is Flutter actually built on? So one of the things Flutter is built on, or used to be built on because Impeller is coming along, is Skia. So you can look it up online, there's nice documentations for it. Skia is this 2D graphics engine which gives you APIs to do graphical operations on multiple different devices. So as the same with CPUs, you have different architectures, you have different things that you need to worry about where you have different operating systems and so on. The same applies to graphics. So if you're running on Windows, Mac OS, different graphics cards, there's all these different things that you have to worry about, and Skia simplifies that by giving you a single API to use. More recently, also Impeller started getting more traction and is mostly ready, or I think is fully ready on iOS and is slowly being supported by more and more platforms, is a new kind of rendering layer that, in a nutshell, allows the Flutter team to do more things. One of those being 3D, which Flutter GPU has shown. So it's extends the specification to also potentially allow more 3D use cases. So we talked about the simplified APIs, but what happens then? So you have Skia, but how does Skia itself work? And to do the last step, don't worry, we don't have to go much deeper. It is actually built on graphics APIs, and these are very, very close to your actual hardware. So if you have a for example, a NVIDIA card or some other graphics cards, there's a bunch of different APIs which are implemented by the respective drivers that talk to those specific hardware components. And they expose a specification. For example, the left one is Metal, which is from Apple, and they make sure that it's always compatible with their hardware. They expose the specification for drawing things, to do 3D, to do all the calculations, because that's what the graphics card is for. It's great at doing matrix multiplications, and not really coincidentally, that's very useful for graphics. There's OpenGL, which is pretty old, but is still widely supported because, I mean, it was deprecated on Apple, but it's still widely supported because it's been around for so long. There's also Vulkan, which is quite a bit newer than that. And those are the things that, for example, Skia and Impeller are built on. So, for example, Skia, it depends on what hardware you're running on. It will either talk to Metal, OpenGL, Vulkan, or some other thing to issue its draw commands. And that's it. We reached the end of the rabbit hole. Thank you very much for listening. And do you have any questions?